This power plant module will start out with a general overview of the engine components. Then we will look at the thrust reverser system, the power management control, and the controls and indicators. We will first look at the general components of the engine. Two wing-mounted CFM56 7B engines produce 27,300 pounds of maximum takeoff thrust. Each engine consists of a dual rotor, axial flow, high bypass ratio turbofan. The engine consists of dual rotors, N1 and N2. They are mechanically independent of each other. The N1 rotor is made up of three main sections. The fan and a low-pressure compressor are driven by a four-stage low-pressure turbine connected by a shaft. The N2 rotor consists of a high-pressure compressor and a high-pressure turbine. The engines are regulated by two dual-channel electronic engine controls, or EECs. There is one EEC for each engine. The EEC uses the autothrottle inputs and the thrust lever position to meter fuel to the engine through the hydromechanical unit, or HMU. Air enters the engine through the air intake. After passing the fan, the air takes two different paths. One path travels into the compressor section and the combustion chamber, where it is mixed with fuel. The resulting mixture is ignited and exhausted. The rest of the air is routed around the engine in ductwork, providing approximately 80% of the thrust. Each engine incorporates a thrust reverser mechanism. The thrust reversers reduce landing roll or the deceleration distance during an aborted takeoff. The N2 rotor mechanically drives an accessory gearbox located on the side of the engine. This gearbox drives fuel, oil, and hydraulic pumps. It also drives an electric AC generator. The engine-driven fuel pump is connected to the accessory gearbox. This first-stage fuel pump increases the fuel pressure and sends the fuel through two fuel-oil heat exchangers. The heat exchangers use oil from the engine and IDG to heat the fuel. This will also help to cool the oil. Next, the warmed fuel passes through a filter that removes contaminants. If the filter is saturated, or a differential pressure is sensed between the inlet and outlet of the filter, the fuel can automatically bypass the filter. But a fuel filter bypass light on the fuel control panel will illuminate. The second stage fuel pump further increases the pressure of the fuel and sends it into the hydromechanical unit, or HMU, through another filter. A portion of the fuel flows directly into the HMU. The rest of the fuel is diverted to another heater before it is sent to the HMU. The heating eliminates any ice particles before the fuel enters the HMU. The HMU meters the proper amount of fuel sent to the combustor. Fuel rate is measured after passing through the main engine fuel shutoff valve. The fuel flow rate can be read on the display unit and is also sent to the flight management system. Engine oil is circulated under pressure. It lubricates the bearings and the accessory gearbox and is used to heat the fuel. The oil quantity is measured as a percentage of the full tank. The oil is pressurized by the engine-driven oil pump that is also run by the accessory gearbox. The oil then passes through the supply filter. An automatic bypass is also installed here in the event that the filter becomes too contaminated. A temperature pressure sensor is located downstream of the oil pump and filter and sends indications to the cockpit. After filtering, the oil travels to the bearings of the engine and the gearbox. Here it lubricates and cools the moving parts. After the lubrication process is complete, engine-driven scavenge pumps draw the heated oil and send it to the fuel oil heat exchangers. After passing through the scavenge pumps, the return oil enters the scavenge filter. An automatic bypass is also installed here in the event that the filter becomes too contaminated. A filter bypass sensor measures pressure at the inlet and outlet and sends a signal to the cockpit, displaying the oil filter bypass alert on the upper display if the pressure differential is too great. The fuel oil heat exchangers are the last step for the hot oil before returning to the reservoir. The fuel oil heat exchangers serve two purposes. The cold fuel draws the hot temperature from the hot oil, thus heating the fuel and cooling the oil. The cooled oil then travels to the reservoir. We will now examine the engine start system. The engine start system uses pneumatic air to rotate the N2 compressor through the accessory drive mechanism. The starter can use pneumatic air from an operating engine, the APU, or a pneumatic air cart. Air enters the starter through an electrically controlled and pneumatically operated start valve. The valve is spring-loaded to the closed position. At 25% N2, the start lever is advanced to idle. This opens the engine and spar fuel valves and electrically opens the HMU shutoff valve through the EEC. Let's take a look at the ignition system. Ignition is used for engine start and various operational reasons. The ignition system consists of two AC igniters in each engine. The igniters are referred to as left and right. The left igniters are powered by their respective AC transfer bus. The right igniters are powered by the standby AC bus. Ignition is controlled by the EEC. The electronic engine control also feeds fuel based on the thrust lever settings into the combustion chamber through the hydromechanical unit. The EECs control the engines through two channels for each engine. Only one channel is used at a time. If the operating channel fails, the secondary channel will automatically take over. The EEC alternates the control channels at each engine start or start attempt. The EEC uses the N1 speed to set thrust using one of two control modes. These modes are normal and alternate. In the normal mode, the EEC uses flight conditions and bleed air demands to derive the correct N1 speed. The EEC will meter fuel so as to achieve this speed. Full rated thrust is achieved at thrust lever angles less than the maximum travel of the thrust lever. In addition, derated thrust can be derived by using fixed or assumed temperatures. Derated takeoff thrust is achieved at a thrust lever angle below the lever angle for full rated thrust. The EEC will provide limit protection for the associated engine. If the thrust lever is advanced to the forward stop, the EEC will limit the thrust to the maximum thrust rating of the engine. The EEC can operate in one of the two alternate modes, the soft and the hard. If the required inputs are not available, the EEC will automatically default to the soft mode. When this occurs, the associated alternate light illuminates on the electronic engine control panel, located on the flight deck overhead panel. The on light remains illuminated in the associated EEC switch. In the soft alternate mode, the EEC will use the last known flight conditions to define engine parameters that will allow the mode change to occur without an immediate change in engine thrust. However, as flight conditions change, there may be engine shortfalls or exceedances. The EEC remains in the soft alternate mode until the hard alternate mode is entered. The EEC is placed in the hard alternate mode by retarding the affected thrust lever to idle or by manually selecting the alternate switch on the overhead panel. In the hard alternate mode, the EEC reverts to the alternate thrust schedule, where thrust is always equal to or greater than normal thrust for a given thrust lever position. The hard alternate mode can be entered by placing the thrust lever to idle when the EEC is operating in the soft alternate mode. The alternate light in the associated EEC switch will illuminate and the on light will remain visible. If the mode is enabled manually, the alternate light in the associated EEC switch illuminates, but the on light will extinguish. The EEC will provide N1 and N2 overspeed protection while it is operating in both the normal and alternate modes. However, the crew is responsible for maintaining the EGT within limits. The EEC will idle the engine at 3 different speeds. These speeds are referred to as ground minimum idle, flight minimum idle, and approach idle. Ground idle is the minimum idle speed required for ground operations. Ground minimum idle helps reduce jet blast and the amount of brakes required for taxi and the landing rollout. Flight idle is the minimum idle speed for most phases of flight. The EEC will provide approach idle when the flaps are in the landing configuration or if engine anti-ice is selected on for either engine. Approach idle provides higher N1 and N2 RPMs than for flight idle. The engines transition from approach idle to ground idle during the landing. The transition occurs approximately 5 seconds after touchdown. This delay keeps the engines at a higher speed in case a go-around becomes necessary after touchdown. In flight, if a fault prevents the EEC from receiving flat position or engine anti-ice status, the EEC will automatically select approach idle when the aircraft is below 15,000 feet MSL. Let's take a look at the thrust reverser system. The thrust reverser consists of two hydraulically operated translating sleeves. When the thrust reverser is deployed, the sleeves move backwards and expose fixed cascade vanes. As the sleeves move backwards, blocker doors deflect the discharged air forward, causing the direction of the thrust to be reversed. The thrust reverser is deployed by raising the thrust reverser lever on the throttle quadrant. The thrust reversers can be deployed provided the aircraft altitude is less than 10 feet or the air-ground sensor detects that the aircraft is on the ground. In addition, the battery switch must be on and the associated engine fire switch must be down. The reverser for engine 1 uses System A hydraulic pressure. The reverser for engine number 2 uses System B pressure. If either hydraulic system is lost, the reverser can be powered by the standby hydraulic system. When the thrust reverser lever is raised, and if all the conditions are met, an electromechanical lock is released. The reverser isolation valve opens, and hydraulic pressure is directed to deploy the system. The reverser isolation valve is powered by the switched hot battery bus. The reverse thrust lever is locked in the reverse idle position until the associated thrust reverser sleeve is more than 60% deployed. When the thrust reverser is deployed, an interlock mechanism prevents the forward thrust levers from moving. The reverser is stowed by lowering the thrust reverser lever to the stow position. This causes the selector valve to direct hydraulic pressure to the stow side of the system. The reverser isolation valve will be held open until the thrust reverser is stowed. Electromechanical locks are then engaged to lock the reverser sleeve into place. When the thrust reverser is commanded to the stow position, the reverser light located on the aft overhead panel will illuminate. The light will extinguish approximately 10 seconds after the thrust reverser isolation valve closes. If the reverser light fails to extinguish after approximately 12 seconds, the engine annunciator light and both master caution lights will illuminate. This indicates that a malfunction has occurred. The thrust reverser system incorporates a safety feature called the auto restow system. This system compares the position of the reverser sleeve with the position of the thrust reverser lever. In the event there is a disagreement between the two, The auto restow system will open the isolation valve and command the selector valve to direct hydraulic pressure to stow the sleeves. Hydraulic pressure is maintained in the stow configuration until the thrust reverser is commanded to deploy or the problem has been addressed by maintenance. Now let's cover the controls and indicators. Engine indications consist of the primary and secondary engine indications. Primary engine indications consist of N1 and EGT and are displayed on the upper display unit. If the upper display unit fails, the primary engine indications will be displayed on the lower display unit. Primary engine indications can also be displayed on either inboard display unit using the respective display select panel. Secondary engine instruments consist of N2, fuel flow, oil pressure, oil temperature, oil quantity, and engine vibration indications. The secondary engine indications are normally not displayed. However, the display select panel and the engine switch on the engine display panel are used to display the secondary engine indications on either inboard display unit or the lower display unit. Engine information is provided by the respective EEC. When the EEC is not powered, N1, N2, oil quantity, and engine vibration information are provided directly by the engine sensors. The secondary engine indications are automatically displayed for one of the following conditions. The displays receive initial electrical power. When a start lever is placed to cut off while the aircraft is in flight. When an N2 is below idle while the aircraft is in flight. Or when a secondary engine parameter is exceeded. When the secondary engine indications are automatically displayed, they cannot be cleared until the condition is no longer present. The fan speed is displayed on the N1 digital display. The N1 indicator is used as the primary engine thrust reference. It is displayed both in numerical format and in analog format using a pointer and a dial. The normal operating range is displayed in white. The operating limit is indicated by a red line. If the N1 speed exceeds the operating limit, the digital and analog indications will be displayed in red. On the ground, after engine shutdown, the same indication is triggered by an in-flight exceedance. A small knob is located on the center forward panel. If the N1 set knob is placed in the both position, the indicator is disconnected from the FMC and position of the reference bug is set manually by rotating the inner knob. Selecting either position 1 or 2 enables the crew to set the reference N1 for each engine individually. When the knob is in the auto position, the FMC information controls the position of the reference bug by using data from the N1 limit and takeoff reference pages. When the reversers are deployed, an amber reverser label is displayed above the N1 indication when the associated thrust reverser is moved from the stowed position. The label turns green when the associated reverser is deployed, indicating that the lever may be moved further to increase reverse thrust. A TAI label is displayed at the top of the analog display. It is displayed in green when the associated CAL anti-ice valve is open. The label is displayed in amber when the associated CAL anti-ice valve is not in the commanded position. Exhaust gas temperature, or EGT indicators, are located just below the N1 indications. The EGT is displayed in both numerical and analog formats. Temperatures are indicated in degrees Celsius. The normal operating range is displayed in white. The maximum continuous value is indicated by an amber line, and an amber band indicates the maximum continuous range. The maximum EGT is indicated by a red line. In the event of an EGT limit exceedance, the digital and analog displays will turn amber or red, depending on which limit is exceeded. This color change is inhibited for up to 5 minutes during takeoff or go-around. On the ground, after engine shutdown, a red box around the temperature indication indicates that an exceedance has occurred. During an engine start, the EEC will flash the box if conditions may lead to a hot start. An EGT hot start limit is displayed when N2 is less than 50%. An amber engine fail label is displayed in the EGT analog gauge when the engine is operating below 50% N2 and the start lever is in idle. The label will remain in view until the engine recovers, the associated start lever is placed to cut off, or the associated engine fire switch is pulled. The next pair of indications are the N2 indications. These measurements indicate N2 RPM and are similar to the N1 indicators and have the same interpretation. A magenta crossbleed label is displayed when an engine is shut down while in flight and a crossbleed restart is recommended. Fuel flow is displayed in numerical format when the fuel flow switch is in the rate position. These digital displays show the present rate of fuel being used in pounds per hour times 1,000. When the fuel flow switch is in the used position, the fuel flow displays will indicate the amount of fuel used since the last reset. The value is displayed for 10 seconds on both fuel flow indicators, after which it reverts back to the fuel flow rate. Placing the fuel flow switch to the reset position will indicate the fuel used since the last reset for 1 second. The quantity then decreases to 0 and fuel flow is displayed once again. Oil pressure is indicated both numerically and with a pointer against a vertical scale. Signals are sent from a pressure sensor and are displayed in pounds per square inch, or PSI. The normal operating range of the oil pressure is indicated in white. An amber low pressure band indicates the oil pressure low range. The operating limit is indicated by the red line. The range of the amber band varies with N2 RPM when N2 is above 65%. This band is not displayed when N2 RPM is below 65%. If the oil pressure enters the caution range, the digital readout and the scale will turn amber. They will turn red if the operating limit is exceeded. Oil temperature indications are similar to the oil pressure indications. Oil temperature information is displayed immediately below the oil pressure displays. Oil quantity information is displayed below the oil temperature indications. Oil quantity is displayed in numerical format. When an engine oil quantity is low, the quantity indication will be displayed in reverse video with a low label. You should note that the oil quantity may decrease significantly during engine start, takeoff, and climb out. Oil quantity may be as low as 0 if the windmilling N2 RPM is below approximately 8%. The engine vibration indications are taken at the number 1 bearing in the engine. These indications are used to compare the level of normal vibration with abnormal readings. If the readings appear to be abnormal, or if a sudden change has been detected, engine malfunctions could be present. Engine vibration is indicated in numerical format and using a pointer against a vertical scale. A tick mark indicates the high vibration level. If the vibration is high, the numerical display will be displayed in reverse video. Crew alerts are displayed on the upper display unit. These alerts are the start valve open, oil filter bypass, and low oil pressure. The start valve open is illuminated amber when the respective start valve is open. The indication is steady when air is supplied to the starter. The indication will flash if there is an uncommanded opening of the associated start valve. The low oil pressure alert illuminates when the associated oil pressure is low. The alert illuminates steady when oil pressure is at or below the red line. The alert will flash when the associated oil pressure is low. The oil filter bypass illuminates for an impending oil filter bypass. Let's take a look at the engine start panel. The engine start panel is located on the overhead panel. There are 2 start switches, one for each engine. An ignition select switch is located in between the 2 start switches. The ignition select switch selects the igniters to be used in both engines. If the switch is in the middle or both position, both the right and left igniters will be powered in both engines. Ignition left selects the left igniter in both engines, while ignition right selects the right igniter in both engines. Each engine start switch has 4 positions: off, ground, continuous, and flight. Ignition is disabled with the switch in the off position. However, both igniters are activated when the associated start lever is in the idle position and an uncommanded decrease in N2 occurs, or when N2 is between 50 and 57%, or in flight when N2 is between idle and 5%. The continuous and flight positions of the engine start switches both provide power to the igniters if the start levers are in the idle positions. Continuous allows only the selected igniters to be powered if the associated engine is operating. While in the flight position, both igniters will be powered simultaneously regardless of the position of the ignition select switch. Placing the start switch to the ground position causes the respective starter valve to open and the respective engine bleed air valve to close. On the ground, electrical power is supplied to the selected igniters when the engine start lever is moved to the idle position. In flight, electrical power is supplied to both igniters when the engine start lever is moved to the idle position. The switch is electrically held in the ground position until the starter cutout speed. The EEC panel was discussed earlier in this module. The EEC panel incorporates an engine control light for each EEC. The light illuminates amber when the associated EEC is not dispatchable due to internal faults. The light operates when the associated engine is running, the aircraft is on the ground, and the aircraft speed is below 80 knots prior to takeoff or 30 seconds after touchdown. The EEC switches control the operation of the respective EEC. The on light is illuminated when the EEC is operating normally. When the on light is not visible, the EEC has been manually selected to the hard alternate mode. Let's take a look at the throttle quadrant. The throttle quadrant incorporates the thrust levers, the reverse thrust levers, and the engine start levers. The thrust levers mechanically control engine thrust. A thrust lever cannot be moved if its associated reverser lever is raised to the deploy position. The reverser lever controls reverse thrust. Reverse thrust cannot be selected if the associated thrust lever is out of the idle position. The engine start lever controls the fuel supply to the engine as well as the ignition. It has two positions, cutoff and idle. Placing the engine start lever to cutoff electrically closes the spar fuel shutoff valve and the engine fuel valve. Ignition is also de-energized. Placing the engine start lever to idle electrically opens the spar fuel shutoff valve in the wing leading edge and the engine fuel shutoff valve through the EEC. The ignition system is also energized through the EEC. This concludes the engines module.